Welcome to Math 151, Rates of Change. Today we'll finish up the material in section 2.2, discussing a few more details about derivatives and how they work. So first of all, remember that the derivative gives rate of change, dy dx if those are the two variables, the rate of change of y with respect to x. So first of all, remember, for a curve defined by y equals some function of x, the difference quotient, change in y over change in x, would be given by the function evaluated at the second point, b, minus the function evaluated at the first point, a. That would be the change in y, divided by the change in x, b minus a. So that gives the average rate of change of y with respect to x on the interval as x goes from a to b. But it's often convenient to define as we've done before. I'm going to make these a little bit bigger. To define as we've done before, let that second point be a plus h. That way the change in x is going to be a plus h minus a, which is just h. And it should be clear that then as h goes to 0 in this expression, then b goes to a. So that gives us two ways then to define the derivative. We can define it as we've been doing, that the derivative at the point a is the rate of change, the instantaneous rate of change of y with respect to x, defined as the limit as h goes to 0 of the difference quotient. That is f of a plus h minus f of a, that's my change in y, divided by my change in x, or equivalently, as we've just seen, I could also do this, and we'll see that this will become handy in the future. The instantaneous rate of change at a, dy dx, is the limit as b gets arbitrarily close to a. So f of b minus f of a is still the change in y, and b minus a is the change in x. Either of these give us the instantaneous rate of change of y with respect to x. We can see an application of this. It's velocity is actually a rate of change. You're probably familiar with the formula that distance is velocity times time, or speed times time. We're going to use the standard physics notation where s represents distance or position, v represents velocity, and t represents time. And we'll work in the standard international units where distance will be measured in meters, velocity in meters per second, and time in seconds. In the case where v is a constant, we can solve for it as simply dividing through by t, s over t, distance over time. But when velocity isn't a constant, when it's changing with time, that would mean also that the position is not a linear function of time. We can compute the average velocity on an interval from a to b, t equals a to t equals b, using our function of position, which now could be curved. The average velocity is still change in position over change in time, and that's the position at the second value of t minus the position at the first value of t. That's my change in position, and b minus a is the change in time. This will give me the average velocity over the interval. If I want the instantaneous velocity, I have to take the limit as b goes to a. As we saw, this is the derivative, s prime of a. So my velocity is the derivative of position. It can be written as the limit as b goes to a of the position at b minus the position at a divided by b minus a. Change in position over change in time. So here's an example. Suppose that the height of an object is given as a function of time by this equation, h of t, that's still a position, right, or distance, 500t minus 5t squared, and this is what the plot of that curve looks like, where h is measured in meters and t in seconds. Then we can determine the vertical velocity as v of t, the change in height with respect to time. H prime of t is simply 500 minus 10t. That's the derivative of h of t, right? If I want the velocity, for example, at 30 seconds, that would be the rate of change of the curve here at 30 seconds, I simply plug in 30 to my velocity equation. So v of 30 is 500 minus 10 times 30. And that's, of course, 500 minus 300, or 200 meters per second. Notice that the velocity goes to 0 at the maximum altitude. That makes perfect sense because what happens to an object? It rises, and then it slows down and stops, and then it starts falling again. So how can we figure out where that is? Well, that happens when the velocity goes to 0. That is when 500 minus 10t is equal to 0. That's easy to solve for t. T is 50. So t equals 50 is the time when the object reaches maximum altitude. And it makes sense. There's the 50 on the time scale, so the maximum altitude is reached there. But what would this mean? If the velocity is the derivative of height, remember the derivative gives me the slope of the tangent line, that would mean that the slope of the tangent line here is 0 at the maximum altitude. And if I want to find the actual maximum altitude, I plug the time back into the height equation. At t equals 50, h is given by 500 times 50 minus 5 times 50 squared, and that's, if you do the arithmetic, 12,500 meters. And it looks about right from the graph. So let's do another tangent line problem. This one isn't related to velocity, but it still has to do with rate of change. For a curve given by y equals f of x, where f of x is 2 divided by the 4th root of x cubed. This is actually one of our problems in our textbook. It's problem number 42. We want to determine the equation of the tangent line at x equals 1. Well, let's go through the steps carefully. First, we need a point, so we want to get the y value associated with x equals 1. Well, I simply plug in 1 to my function. That's 2 divided by the 4th root of 1 cubed. Well, 1 cubed is 1, and the 4th root of 1 is 1. So this is just 2 over 1, or 2. So the point 1, 2 is on the curve. Next, in order to find the slope of the tangent line, we need the derivative, so we want to compute the derivative, f prime of x, or dy dx. Well, this is not in a form where we can compute the derivative, so we change it. Remember, taking a root is a fractional exponent, so this is actually 2 divided by x to the 3/4, the cube, and then 1 over 4, or 1/4 gives me the 4th root. So this is 2 over x to the 3/4. That's still not in a form I can take the derivative. So I remember that dividing gives me a negative exponent. So this is the same as 2 times x to the negative 3/4. And now the function is in a form where I can apply the power rule. So f prime of x is 2 times the derivative of x to the minus 3/4. Well, that's minus 3/4 times x to negative 3/4 minus 1. I always subtract 1 from the exponent. Well, minus 3/4 minus 1 is minus 7/4. And of course 2 times minus 3/4 is minus 3/2. So the derivative is minus 3/2 x to the minus 7/4, which is, if we wanted to do it in root form, this would be minus 3/2 times 1 over the 4th root of x to the 7th, right? But this is okay for calculation, so we'll leave it this way. So now that we have the derivative, we can find the slope of the tangent line, which is the rate of change of y with respect to x at x equals 1, by plugging 1 into my derivative. So m is f prime evaluated at 1. That's minus 3/2 times 1. Well, 1 raised to any power is 1, so it's easy in this case. So it's minus 3/2 is the slope of the tangent line, which is also the instantaneous rate of change dy dx. We need one more thing to have a line equation. We need the y-intercept. And so I get a y-intercept by taking a y value minus m times the associated x value. Our y value is 2 minus our slope of minus 3/2, and our x value was 1. So this is actually 2 plus 3/2, which is 7/2. So the tangent line is given by y equals minus 3/2 x, a negative slope, plus 7/2 for my y-intercept. How do we verify this? Well, we plot the curve and the tangent line together. You can do that on your calculator. Here is the original curve plotted with, which is f of x equals 2 times x to the minus 3/4. And here's my point of tangency at x equals 1, y equals 2, and there's the tangent line. Y equals minus 3/2 x plus 7/2. And it looks proper, and you can verify that it really is the right answer. Okay, so that's a good review of this material. Now you can get some practice with it. Okay, so first a new velocity problem. Given the height equation, h of t is t squared minus 60t plus 925. First determine the velocity equation, that's just the derivative of the height equation. Determine the velocity at t equals 200 seconds. Determine the time when the velocity reaches 0. That's going to be solving h prime of t equals 0 for t. That's not plugging t equals 0 in. That's right. We want to find the t that gives h of t equals 0. And then determine the height at the time when the velocity is 0. That is, use the t you found in step 3 to figure out what the height is by plugging that back into the height equation. So please pause the video here. Work these exercises. You can use your textbook, Chapter 2.2, as a reference. And when you've completed these exercises, continue the video and we'll reveal the solutions. Okay, well, hopefully you did that work. You paused the video and found solutions. Let's compare answers. Well, first, if I take the derivative of h of t to get the velocity, the derivative of t squared is 2t. The derivative of minus 60t is minus 60, and the derivative of a constant is 0. So there's my velocity equation as a function of time. Notice it's a linear equation. What's the velocity at t equals 200 seconds? I simply plug 200 into my velocity equation. 2 times t minus 60, 2 times 200 minus 60, and the arithmetic says that's 340, 400 minus 60. Determine the time when the velocity is 0. That means I have to solve the equation 2t minus 60 equals 0. So that's simple. I put 60 on the other side, divide by 2, and it's clear that t equals 30 is a solution to v of t equals 0. And then finally, determine the height at that time. Well, we just found that the velocity is 0 at t equals 30 seconds, so we plug 30 time equals 30 into my height equation to figure out the maximum height, or actually the minimum height in this case. So h of 30 is 30 squared minus 60 times 30 plus 925. That's plugging 30 seconds into my height equation, and you get 25 meters. And here's the graph of that function. Notice it's a right side up parabola, so we start out at 925 meters and then fall all the way down to 25 meters here at the bottom, and then we go back up. So this might be on a spring or something that's making this object do that. Well, hopefully you found those solutions. Remember, using the graphing calculator really helps to verify your work. Let's do one more exercise. This time a tangent line problem with fractional exponents. So given the function f of x is x to the 2/3 plus x to the minus 2/3, determine the equation of the tangent line for the curve y equals f of x at the point associated with x equals 8. Plot the curve and the tangent line using your graphing calculator. So again, please pause the video here. Work this exercise. Again, you can use sections 2.1 and 2.2 as a reference. And when you've completed this work, continue the video. Okay, hopefully you were successful at that. let's compare answers. So what do? First thing we do is we find the y associated with my x. So I plug 8 into my function. That's 8 to the 2/3 plus 1 over 8 to the 2/3. Remember, x to the minus 2/3 is 1 over x to the 2/3. Well, what we're doing here is we're taking the cube root of 8 squared. The easy thing to do is do the cube root first, and the cube root of 8 is 2, because 2 cubed is 8. So this is the same as 2 squared plus 1 over 2 squared, because the cube root of 8 is 2. And arithmetic shows that's 4 plus 1/4 is 17/4. So this is my y associated with x equals 8. That is the point, I guess we can indicate it here, is the point with coordinates 8, 17/4. So now, determine the derivative. That's what we need to find the tangent, the slope of the tangent line. That's easy. We use the power rule. So it's 2/3 x to the minus 1/3. And remember, now this is in the form where we can easily take the derivative. Minus 2/3 times x to the minus 5/3. Because when I subtract 1 from negative 2/3, I get minus 5/3. So this is the derivative function. And then to get the slope, we simply plug m. To get m, we plug the x value into my derivative. So the rate of change, instantaneous rate of change of the function at x equals 8 is f prime of 8. Well, I plug in 8 again. This is 2/3 times 1 over x to the 1/3. So that's 2/3 times 1 over 8 to the 1/3. Minus 2/3 times 1 over 8 to the 5/3. Well, again, we use the fact that the cube root of 8 is 2, so this is 2/3 times 1/2. And here we do the cube root first, so this is 2/3 times 1 over 2 to the 5th, which is 32. So canceling things out and doing the math, we find that this is 1/3 minus 1 over 3 times 16, and that's 5/16 if you do the arithmetic carefully. So the slope of my tangent line, f prime of 8, is 5/16. We find a y-intercept in the usual way. We take a y value minus m times the associated x value, so 17/4 minus 5/16 times 8, that's actually 5/2, and we do that arithmetic with a little care. We see that the y-intercept is 7/4. So the line equation is y equals mx plus b, y equals 5/16 x plus 7/4. How do we tell if we did it right? Well, we plot both the original function, f of x, and this tangent line using a graphing calculator or a program like this one, and you should get a picture that looks something like this. Here's my point of tangency at 8, what was the point? The y was 17/4, yeah, a little bit more than 4. And then here's the tangent line. It looks like a tangent line. Notice in this case, the tangent line actually crosses the curve. That's okay because the curve is kind of curving up and then curving down here. It crosses it over here, but it's tangent in the place where it has to be. Okay, so hopefully you found this useful and that you found this solution. So for homework, please study sections 2.1 and 2.2 carefully. We'll have a quiz on this material focusing on 2.2 on Monday. And complete the homework quiz on D2L before class on Monday. That'll be posted and I'll notify you when that quiz is available. That'll give you some practice before our real 10-point quiz on Monday. That ends our lesson for today.